So lesson one is a review of ratios and proportions. So number one here, what's the main difference between a ratio and proportion? This will be a little bit overgeneralized, but a ratio is a comparison of two numbers. There's kind of three main ways to write a ratio. Say 1 to 3. You can use the colons. You would still say 1 to 3. Or what we will mostly use is the fraction, like 1 over 3. Right? Whatever's on bottom was 3 times as big or 3 times as far. Ratio. Proportion, on the other hand, is an equation of two equivalent ratios. Usually they're written as fractions. For instance, 1/3 equals 2/6. That is a proportion. They are proportional to each other. So if one pizza cost $3, two pizzas cost $6, that would be proportional. That's where that word comes from. And it just means that they're equivalent to each other. So one of the main uses of proportions has to do with scale drawings. When I talk about a scale drawing, there's kind of three main scale drawings that are used all the time. A map is a scale drawing. Obviously it uses a really big scale because it takes, sometimes the world and puts it on a piece of paper. So a scale drawing could also be a blueprint of a house, or it's often used in kind of like construction. Maybe it's not of the whole house, but maybe it's of a part, or maybe you're a furniture builder and it's a scale drawing of the piece of furniture that you're building. So, but the question here asks for what is the use of a scale in a scale drawing. A scale is used to convert between the size of the drawing. So maybe something measures 1 inch in a drawing, and the actual size. So maybe in real life it's a foot long. So a scale is used to convert between the size of the drawing and the actual size of an object. One more thing I want to add up here to ratios, just so you know up here. Generally, when they ask you for a ratio in the problem, two things that you should know. They want you to convert them so they end up being unitless. And they also want them to give in reduced form. So for instance, if in the problem the ratio was 2 to 6 and they ask you for the ratio, they want you to give 1 to 3 as your final answer. This is usually, if they ask you for a ratio, they usually want it in the form with the dots in between, but all the forms are equivalent and I don't care what form you give it in. Okay, so there's the basics. So let me go through some examples. I'm going to start with proportions. So other notes. Example. Show that the extremes, I'll talk about what that is, of a proportion are equal. So I'm going to start with proportion. I will explain what extreme is in a minute. So 1/3 equals 2/6. Right? That's a proportion. I have two equivalent ratios. 1/3 is equal to 2/6. Hopefully we all know that. So what are the extremes? The extremes are also known as cross products. So 1 times 6, that's a times sign, which is 6, is one of the extremes. The other extreme would be 3 times 2. It also equals 6. If you have a true proportion, the extremes are always equal, which is pretty cool. It doesn't matter how complicated of fractions you make. So let's say I had 5 over 20. Let's see, what else would be equivalent to that? 30 over 100. No, 30 over 120? Is that even right? That can't possibly be right. So hold on, let me think again. Yeah, those are right. I mean, they both reduce. So let's check our extremes. That's the easiest way to check. So 5 times 120 comes out as 600. 20 times 30 would be my other extreme. It also comes out as 600. Woot! They come out the same. Knowing that the extremes of a proportion are equal is why we can what they call solve proportions. Let's say I knew a ratio of something. I knew the ratio was 3 to 5. But I want to know, I don't know, we'll say 12 and x. I need to figure out what x equals. Well, 3 times 12 is 36, and 5 times x is 5x. I don't know what x is, but I know that those two have to be equal. Now I have an equation that's pretty easy to solve. Divide both sides by 5, and I would get 7.2 equals x. It doesn't matter if it's more complicated than that. So let's say I have 2 out of 7 equals x plus 1 over 3. I still need to know my extremes. So 2 times 3 is 6. 7 times x plus 1 is 7x plus 7. Do make sure that this arrow gets distributed to both of the terms. From here, solve it out and subtract 7. So negative 1 equals 7x. Divide by 7, which gives me negative 1/7 for x. Okay, so those are proportions. Not only are the extremes true, there's a nice box on page, I think it's 417. It's a yellow box. They go through a lot of different things you can do with proportions other than extremes. So I'm going to be pretty basic. A over B equals C over D. Instead of using real numbers, I'm just going to kind of go through some options. Know that if A over B is C over D, you could flip them upside down, right? That would be the same. You could kind of rotate them. I'm trying to think. It's not really rotating, it's kind of reflecting. I'll kind of explain this in a minute. So A over C and B over D. So I'm going to draw some arrows. If I know A goes to C and B goes to D, A goes to C, B goes to D, right? I have it, my arrows still line up, they're parallel. It doesn't matter which direction I go. A to C, B to D. Notice the lines are still parallel. Let's see, there's one more way I could do them, right? Because I could put the C on top, and I can even put the C over on the other side. A goes to C, B goes to D. There's lots of different ways to write a proportion, so just know two people could be solving the same problem and write the same proportion in different ways. There's 4 ways of doing it, just offhand. There's 8 different ways because you could also change which one's on the right and which one's on the left. You're not limited to just doing that. I'm going to kind of explain this in terms of this first problem. You just have to be consistent. So think of A as top and B as bottom. So top plus bottom over bottom. Right? That was top plus bottom over bottom. As long as I do the same thing on the other side, it's going to be equivalent. So I said top plus bottom over bottom. So C plus D over D is equivalent because I'm doing the exact same thing on the other side. Just know there's lots of weird things that you can do with proportions that are pretty cool. So let me go through some kind of examples of kind of nuts and bolts. So example, on one drawing, 1 inch represented 1 foot. Give this as a ratio. And implied is I want it to be unitless and I want it to be reduced. They don't always tell you that in the problem, but they always say that. So some people will just be, well, 1 inch and 1 foot. But that doesn't really work because a ratio, once you have a plane ratio, this is a scale rather than a ratio. A scale is a special type of ratio. And a ratio can be used as a scale, but a scale isn't a unitless reduced ratio. When they want it to be unitless, it means I have to change them to the same unit. So instead, I want it to be 1 inch is 12 inches. Once the units are the same, I can drop them, and that's a 1 to 12. 1 inch representing 1 foot is a 1 to 12 ratio. Why would we want it as 1 to 12? Because without thinking, I know that one is 12 times bigger than the other. Right? It doesn't matter if the first one started in miles, the second one would be in miles, 12 times bigger. If the first one was in feet, the second one is feet, 12 times bigger. I've taken out of the fact that it had to be in inches. So now I can work in centimeters, I could work in meters, I could work in any unit I wanted. And I know the ratio. As far as reduced, 1 over 12 as a fraction, that doesn't reduce. So it is already reduced. Now you might want to pause to get this written out. I wrote out this example while not recording to save a little time. So in a shop, a scale of 1/4 to 1 foot, so there's my ratio, my scale, is used on drawings. Use this scale to find the actual dimensions of an object that measures 2.5 inches by 1 inch on the drawing. So one of the things that confuses people about this is that this is actually two separate problems. You have to figure out how far 2.5 inches is on the drawing and 1 inch separately. Some people are able to do that pretty quickly in their head. If you really understand a ratio, you should be able to do that. If you can do that, go ahead, do it. It's fine to do it that way. I'm going to show you how to do it otherwise. They tell us that 1/4 inch is 1 foot. And so the first problem, I'll call it the yellow problem here, is that 2.5 inches is what? So notice I'm not in unitless. I didn't convert it to unitless. I could have, I chose not to. So I need to put that in feet. My answer is going to be in feet. You can think of the arrows as basically giant equal signs. You don't have to do anything special. And this is why we understand that extremes are equal. So 1/4 times x has to equal 2.5 times 1, which is 2.5. Divide both sides by 1/4, and I get 10. So that first dimension is 10 feet, because a 1/4 inch fits into 2.5 10 times. Going on the other one, I have the blue one, I wrote it down here, is 1 inch. It's the same problem. 1/4 x equals 1 times 1 is 1, and that gives me x equals 4, so 10 feet by 4 feet are the final dimensions to that problem.